Hello, and welcome to this video on the hierarchy of academic evidence. Reflecting on comments made recently, the realization hit that the way academia views and attributes value to published work may not be fully understood. To give some background to this, there are between 6 and 10 categories that a piece of research can fall into. The first of these are case studies, opinion papers, letters, and literature reviews. These come into background. The newest and most cutting edge in evidence often falls into the second of these, original or primary research. Next are the case control and cross-sectional studies, followed by the cohort studies, then randomized trials, which are followed by population studies, though they often share the same tier. Finally, the meta-analyses and systematic reviews. These terms may not be familiar to you, so this video will explain what they are and what they mean. The first level is foundational. Foundational because it is intended to be the equivalent of conversational topics or very low-level understanding. Textbooks and medication information sheets are examples of this. This is also exemplified by studies of frontline events in academia and the larger environment. Examples include the thalidomide case studies and early observations of polar bears crossbreeding with grizzly bears. These are often 1 to 5 patients, or events observed in isolation for case studies. These identify prospective topics and research areas. It is very much like prospecting, but for ideas. Like prospecting, the ideas often fail to lead to anything more substantial. The problems with this level are many, but the most obvious issues are centered around the sample. The size is small, and the publication normally occurs due to opportunity and interesting outcomes, not necessarily planning. This leads to a biased sample, both the researcher's bias in the sampling and the sampling itself. These studies also tend to be retrospective in nature. There is an axiom that goes along the lines of, everyone has 20/20 hindsight, and this is especially applicable to retrospective studies, where examining what has occurred and knowing what the outcome was beforehand creates a false representation. This level is often either not peer-reviewed or assessed to a different standard. These articles, case studies, and letters need to communicate the message rather than the methods, results, and conclusions. They are often an expert highlighting a concern, the next level of research, or an event that a researcher feels warrants the interest of the wider academic community. These observations can lead to cutting-edge or primary research. Examples of this include the use of certain blood pressure medication for certain racial groups. Others are the direct sampling of glaciers and core drilling in environmental change. These are largely observational studies. Observational studies have little or no controls in place. There are no independent or dependent variables. There is only an outcome that can be seen and speculated about. These studies give an idea of what might be the cause and effect relationship, but it is rather nebulous, without specific details and understanding. More novel studies, such as drug development or molecular biology, follow an evidence-based approach. This is slightly better than the observational studies. The difference lies in the ability to control for variables. It has an independent and dependent arm. There are controls and null hypotheses built into the research design. The problem here is small sample size and sources. With a very generous upper limit of 100 or less, this type of research is subject to severe bias if samples are from a small area, low population density, or inbreeding, among other issues in the case of genetics. It adjusts for these in isolation and produces a one-off set of results. These can be subject to the effects of chance. This is why studies should be, and sometimes are, replicated by other researchers, where possible. This level is generally published as peer-reviewed articles. You can see an example of this here, and beside it, you now see a case study. The difference is in the depth of information, methodologies, and the kind of results that can be drawn out from this, and the conclusions that are made. This obviously leads to the next level up, that being the cohort study. Cohorts are large groups of between 100 and 300. In some cases, it can be as high as thousands, especially so in drug trials. Cohort studies begin to remove the issues of sampling biases. If you have hundreds of people being sampled, there is likely to be something to the results drawn out if they are consistent. However, this is also subject to other sampling issues. These studies tend to lose numbers very quickly due to the difficulty in following up and keeping tabs on people. It is especially hard when they are volunteering for research. This means longer-term studies fail to have the same rigor as the earlier study components do. You can see that here with the numbers as they drop out of the study. This kind of study is better than the lower levels when it works, but it can quickly lose the advantage as its numbers drop below those thresholds. Cohort studies are used for intergenerational and long-term provisional results. The Simpsons used this as a joke in one episode, where the researcher followed the progress of the town's inhabitants. As was demonstrated in The Simpsons, the actual outcomes are completely uncontrolled for, and therefore a cohort study often has very open ends on it, which are unreliable and not necessarily as useful in the case of a predicting model. The next level is a randomized controlled trial. These methods are used for population level studies as well. It has two key aspects. The first is that a sample is random. The sample is not controlled by the researcher, but is the practical equivalent of pulling names from a hat, where one group is put into an experimental program and the other is put into a control program. This is then coupled to the second aspect. The randomly selected participants are matched to an age, gender, race, and more characteristics individual. This means the results from the first person can be measured against the second, who is a hypothetically healthy, normally distributed person without the variables of the sample population. For example, autistic children could be compared with age, gender, race, and location-matched healthy, normal children. Many developed nations have registers of the medical care given to anyone born in the last 20 years and for anyone who has received public health care in the same time. This comprehensive dataset allows a good data scientist to account for as many variables as humanly possible and create these matches. These national level programs tend to be used for population studies rather than for a randomized controlled trial. This kind of study is heavily limited by data availability and participant viability. The population of a developed country is large, and the available information is simply unwieldy. Large data processing capacity is needed, but not only large data processing, the ability to account for this and conflating variables. On the other hand, underdeveloped nations do not have this comprehensive data. It means adjusting for national level sampling can be hard. It also makes population differences, such as environment, diet, or infrastructure, more of an issue. Looking at diabetes, these could be the difference in the availability and use of medication and diagnostic methods and equipment. Much of this is sorted by using a population comparison in like countries. For example, a Danish study may look at a German study or a British study for its results, and then say European populations can have this particular conclusion drawn about them. This is also why systematic reviews are used. These tend to summarize the available evidence from the highest quality studies. These studies set criteria beforehand. They then collect all of the accessible articles and measure them against this criteria. These are normally a minimum of methodology standards, participant numbers, and years since publication. They cull the articles that fail to meet these standards. They then take the methods, results, and conclusions. These are distilled and consolidated in general trends and topics. It creates an overview of the best research in an area of interest to the author and the reader. It then also places the information into the context of the existing literature. This means that single, isolated studies with anomalous results are weighed against the bulk of findings. In other words, what produces the most reliable model of predicting events based on observable and recordable data that fits into the larger picture consistently and reliably. The problem here is the lack of original research and the obvious limitations in sampling every published article. The volume of articles is nearly impossible to read and more difficult to obtain with limited databases available for a reasonable cost. This is where the last category comes in, meta-analyses. These take the data from the same quality of studies as those used in systematic reviews, which is the best possible studies with the most reliable possible methodologies and data in them. The difference is that the meta-analysis examines the data set and produces original research, whereas a systematic review only presents the fundamental findings from that research. The meta-analysis takes large data sets that could not be economically produced for an individual study, but can be when used as a combination of the data sets from both geographically and time-separated studies. This removes many of the sampling issues seen in previous study types. The large number and locations make the results drawn from these more reliable. This is due to the difference in how random sampling, researcher bias, and sampling locations effect is minimized. As you can see, the basic level case study and primary research is essential as it provides leads and evidence for the field. It means that experiments and results can be validated by other researchers. It also has significant flaws. This leads to the need for more comprehensive and reliable study designs. These designs culminate in systematic reviews for information and meta-analyses for data. This is why the pyramid exists as a representation of the academic evidence hierarchy, and why greatest weight is given to certain kinds of studies over others. Thank you for watching this video. Please post any comments, questions, or suggestions you may have below.